Welcome back to our course in Introduction to Quantum Mechanics for computer scientists, for computational biologists. In the last lecture, we went through some virtual experiments, which summarizes the results of many actual experiments that had been performed over the last century, essentially, which highlights highly counterintuitive properties of subatomic particles. And we were discussing in particular the double slit experiments, where you have some kind of source emitting different kind of objects, let it be guns emitting bullets, or some kind of device producing waves, or even a cathode emitting electrons. And all these particles or waves are then let propagate freely in space until they impact a screen, which contains one or two holes that can be open or shut. And then they are detected on a screen. Of course, the technologies and the methods we use to detect this on the screen may vary depending on what you're trying to detect. In particular, if you're detecting particle bullets, it's sufficient to have like a wooden panel in the end here and count how many particles actually reach in a given position. If you have an electron gun, we can think about detectors of electrons covering this plate. And these are devices that emit an electromagnetic impulse anytime an electron actually reaches the board. We distinguish two main behavior by looking at the example of the physical gun and the wave, which are representative of ballistic and wave behavior. And these two behavior is all there is in classical mechanics. Something is either a particle, that is, it follows the ballistic behavior, or a gun, or a wave, in which case it doesn't follow the ballistic behavior. Remember, our way of distinguishing between ballistic and non-ballistic was like to compare the probability of observing a particle at a given position in the screen and relate it to the probability of observing the particle on the screen when only either of the two holes is left open. Now, if you have a ballistic behavior, the probability of finding the particle on a given position in the screen when only one of the two holes is open, plus the probability associated with the other hole being open, add up and give the same result as the probability when both holes are open, which we interpreted as an evidence of the fact that the bullet goes through either holes represents a disjoint event. Either the electron goes through hole one, the bullet goes through hole one, or the bullet goes through hole two. And therefore, our result is something like a nice double hump structure. We then analyze the case of a wave, and the wave clearly defeats this simple idea of disjoint events because a wave is passing at the same time through both holes, generating circular waves on the way out. And if the wavelength of the wave and the width of the slit are suitable to, then what you find here is a very different behavior, which is characterized by the presence of interference patterns. Okay. This nice separation between wave-like behavior and particle behavior is well understood in classical mechanics because waves and particles are clearly radically distinct physical objects. But as we approach the microscopic world, things get messed up. In particular, when we discuss the case of an electron gun, we repeated the same experiments and we came to the conclusion that there were features that sort of resemble the ballistic behavior and features that resemble the wave behavior. In particular, unlike waves, detectors were shining one at a time, which means that the electrons arrive at a given time in a given position. That's not how a wave behaves. A wave arrives gradually, has a peak, and then disappears. So it arrives with a continuous time distribution, and it arrives with a continuous space distribution, with the wave being more intense in the detector, slightly less intense in other regions, maybe with interference patterns. So really, we are monitoring this being completely opposite scenario, and electrons seem to have particle behavior. However, on the other hand, they do not obey the ballistic rule that the sum of a probability when both holes are open is simply the sum of the probabilities when either hole is open. So this is the violation of this simple principle of ballistic behavior is a signal that the electrons are not completely ballistic particles. And in particular, that the notion the electrons is either in hole 1 or in hole 2 seems to be violated because the violation of the ballistic rule simply implies that the event passing through hole 1 and the event passing through hole 2 are not disjoint. You can pass through both holes at the same time somehow. Then the question arises, how come the electron arrives in the final screen in one specific location at a given time, but for some crazy reason, it doesn't like to pass through some intermediate screen in a particular hole rather than the other? So how come it's ballistic only in the final screen, but it seems to be wave-like in the intermediate screen? I mean, how can the electron know when it has to be ballistic and when it has to be wave-like, right? It looks like a contradictory behavior. Either the electron behaves like one particle or behaves like the other, or like a wave. So how come the electron behaves like a particle in the second screen, but like a wave in the first screen? To try to shine light on this question, we imagine placing like a small device here, which is able to detect if an electron is passing nearby. And if the distance to which these devices, which we call the lamp, the distance to which they can be sensitive for an electron is limited, the range of sensitivity is limited. So when the electron passes through, say, hole 1, only lamp 1 shines and lamp 2 doesn't shine. And conversely, when the electron goes through hole 2, only lamp 2 shines and lamp 1 doesn't shine. So this way, we are able to see if whether it is actually true that the electron is passing through the intermediate holes at the same time as the violation of the ballistic rules seem to imply. Well, if you do that, you discover that contrary to what we expected, the electron does pass through one of the two holes exclusively. So it does have a ballistic behavior even here. But then how come the ballistic rule is violated? Well, it turns out that if you do these experiments in which you not only detect the position of the electron in the final board, but also detect the position of the electron in the intermediate wall, then the interference pattern disappears and one recovers a nice expected ballistic behavior. So if we want to measure the position in the final screen only, then apparently the electron behaves like a wave in the first screen. But if we try to pin down the position on the first screen, we discover that the electron behaves like a particle, and the interference patterns, the wave behavior disappears. So apparently, whether the fact that the electron is a wave or a particle is not an intrinsic inherent property of the electron, but rather it is a property that the electron reveals depending on what kind of measurement you do. So the fact of measuring the electron reveals specific properties of the electron, and the electron behaves as one entity, particle, or another entity, a wave, depending on what I'm trying to look at, what kind of property I'm trying to reveal. Obviously, this is entirely different from what we expect from our experience in classical physics, in the microscopic, macroscopic world, where something is either in a room or is not, something is either heavy or is not, either there or it's not there, right? We never have something that is, say, in the room or not, depending whether I measure it. So this fundamental principle that measurements affect reality is an entirely new concept in quantum mechanics. So somehow nature, in classical physics, you have nature, and then you have measurement, and measurement is something you do a measure, and you get the information, and you get information about nature, so to say. In the microscopic world, instead, nature and measurement are strongly entangled. They're basically part of the same world. And you cannot measure a system without changing or affecting its nature. You cannot measure a physical system without changing its nature. So that was the big sort of revelation, if you want, that the virtual experiments we discussed last time was giving us. And we concluded last lecture by trying to sort of interpreting this result. And we did that with an analogy, if you want, entirely classical, but somehow this analogy has the virtue that it somewhat is able to reveal some feature that are also there in quantum mechanics. And the analogy was that of measuring the position of a basketball in the room, more or less like a bat would do it. A bat will throw waves and record the acoustic wave and record the time of arrival of and the direction of the arrival of the reflected wave, and use this information to reconstruct vision, which is essentially the same thing the actual light-based vision is doing. You detect photons that have been emitted by the source, and you're able to reconstruct the information of where this light is coming from, and therefore forming a shape in your mind, right? Post-processing this electromagnetic information, our brain forms an image. You can do that with acoustic waves. So rather than doing that, we were thinking of imagining of throwing little ping pong ball in the dark in a room and recording this noise of object that this ping pong ball may impact on, or even trying to record where the ball has gone. But let's say we record a noise. Now, if you're hitting a heavy object with a light object, you record a noise, and you can be pretty confident that the object is still there after you record a noise. So you have not perturbed the object by measuring it. But on the other hand, when you try to record the noise produced by another ping pong ball when it's hit by the ping pong ball you're using as a probe, then you run in a different situation in which the effect of measuring the position of the second ping pong ball ultimately results in having changes states, and you don't know anymore where the system is after the measurement. So this is an example that illustrates how measuring a system alters its state. And this is occurring whenever the probe and the particle being probed are both of the same size. Now, when you're looking at the microscopic world, you're not in such a scenario because photons, for instance, they can be reflected by microscopic objects, but microscopic objects do not move or change their significant state because of the reflection of that same photon. But when you try to measure an electron with a photon, you really are in the regime where you're trying to measure a ping pong ball with another ping pong ball, and they're both comparable in size and energy scales, as a result of which the effect of measuring the electron changes somewhat, affects the electron itself. Now, this is nice, but it doesn't certainly explain why the electron changes nature from being a wave and a particle. Why does it do that? And let me tell you from the very beginning, there's no way you're going to understand it. Nobody understands. There's no way you can understand this phenomenology based on some basic intuition you might have. It is what it is. We just have to accept it. So now this should make sort of, I think this point raises a discussion. When we see something in the microscopic world, we think we understand it, but what we say we understand it, it really means it makes sense with a collection of experiences we've gathered in the past. Say, I measure the position of a basketball ball and I know where it is. And when I told you this virtual experiment of throwing ping pong ball to detect where the basketball ball was, I think it made sense to you. And you think, okay, I understand this. But you understand means that you can relate this notion to other experiences you had, which provided similar outcomes. I remember when I said, when we are 2 years old, we smash things, we throw things, we chew things, we interact with macroscopic objects, and we build our intuition. And this intuition that we build is what we ultimately consider as understanding something. But we don't have the experience of understanding in this very empirical way the microscopic world, because we are not microscopic particles and we are not microscopic even when we are 2 years old. So whenever we interact with the microscopic world through tools, such as an electron gun, we are interfacing ourselves outside the comfort zone of our physical intuition. So there's no really way that the impression of not understanding is basically the fact that we do not relate that to any experience we have in our brain already installed. So there is really no hope for understanding when you're trying to be objective and make a measurement. You can only record the result of these measurements and try to build a theory that accounts for them and predict outcome of future measurements and future setups. And that's all that science can be all about. So one thing that became evident with quantum mechanics that wasn't as evident before quantum mechanics is the fact that quantum mechanics, and I would say since quantum mechanics is very fundamental in physics, the most fundamental, or at least people claim about quantum gravity, but who knows what happens at those energy scales. I don't think we are in any condition to say anything about the Planck scale, whether quantum gravity, strings, or whatnot will happen. No experiment can probe that. Since no experiment can probe that, I don't talk about it. Okay? So as far as testable theories is concerned, quantum mechanics is a fundamental theory today. And in quantum mechanics, and therefore in all the physics that follows from that, we have a clean statement that it wasn't so clear in classical mechanics. That is, quantum mechanics is not a theory of nature. No, quantum mechanics is a theory of performing measurements on nature. I mean, I would like you to spend a minute in trying to think about this huge epistemological difference between giving up the idea that I understand nature, because I can never understand nature if I have to interact with nature with probes. All I can possibly do in science is understanding the result of making experiments on nature. So understanding the outcome of measurement. And it's an entirely different story. So if you want to be a little bit philosophy driven, you may say science decouples from natural philosophy with the rise of quantum mechanics. Einstein was a natural philosophist. He believed humankind could understand nature. But after him, and after the development of quantum mechanics, it became clear that science is not about natural philosophy, at least within the framework of quantum mechanics, is about much more or less ambitious task of understanding what happens when you try to perform measurement and therefore when you try to interact with nature. Okay? So, in this perspective, we have to develop the theory that accounts for the evidence provided by the double slit experiment. And there's nothing more deeper to understand. You just have to develop a theory that accounts for that, giving that for granted if you believe the experiments. And in 2020, we believed over 120 years of experiments on that. Okay, very good. Now, the goal of these lectures is to provide you with additional surprising evidences that contradict the classical intuition. Now here is another one. This is called the Stern-Gerlach experiment. Stern-Gerlach. So what is a Stern-Gerlach experiment? Well, it's again the experiment you have when you have a gun, and this gun is emitting atoms or electrons. The important thing is that the particle that this gun is emitting must be equipped with a magnetic moment. How do I know a particle has a magnetic moment? Well, it interacts with a magnetic field in a specific magnetic moment, magnetic field interaction. You know, the energy of interaction of a magnetic moment with a magnetic field is given by this expression. And that's why the compass points towards the north, because it minimizes the energy, right? So you have a gun emitting particles with a magnetic moment. And then you have this beam of particles passing through a device which generates an inhomogeneous magnetic field. Now, the details of why you need an inhomogeneous magnetic field and how this magnetic field should actually look like are irrelevant for our discussion. The only thing that is relevant and that you can orient this device in different angles. You can put it vertically, horizontally, or in this direction, and any angle in between. So this magnetic field here can be changed. And you can place many of them. On a row, for instance. Okay? And then, of course, you can put a screen or a detector here to see what happens to your beam. So obviously, if you shut off the magnetic field, let me just put my apparatus here like this, but there's no field inside, then obviously the electrons will not interact with anything, they will continue, and in the end, I will detect the number of electrons. Now, this will be strongly picked, so to say, if the beam is strongly focused, right? Now, what happens when I start lighting up a magnetic field in here? I turn the machine on. Well, in classical mechanics, I expect that the interaction depends on the orientation of the magnetic moment of my particles. So in particular, there will be some electrons that will have a magnetic moment almost aligned with the velocity, so vertical with respect to this plane, and they will be basically left unchanged, and they will continue to go straight. There will be some particles with a magnetic moment that is more pointing in one direction, and they will deflect it because of this interaction in this direction. And there will be particles with a magnetic moment oriented in the opposite direction, and they will be deflected in the opposite direction, more likely. So what we expect to find from our basic intuition is that there will be a distribution of deflection, and maybe this will result in something like this. Why? Because, you know, if I do nothing, then basically this width is simply the width of the beam, and we can take it to be as small as we want. But when I switch on the magnetic field, clearly the fact that some spins, some magnetic moments are pointing in one direction and in the other direction is responsible for deflecting more. And so, you know, since the angles can be anything, we expect the deflection to be arbitrarily strong, and the result is something like a broad curve. That's what we think we are supposed to see. And guess what? This is not what is seen in real experiments. In real experiments, what you see is two large peaks and nothing in between. So radically opposite. And the position of these peaks is compatible when you crank up the numbers with a scenario in which all the particles that are passing through the magnet are either completely aligned with the z-axis or completely anti-aligned with the z-axis. So here is where the aligned go, and this is the anti-aligned. So this first piece of evidence tells us something that we did not expect. Somehow, magnetic moment the z component of the magnetic moment, because this is the one that interacts with the field. Remember, if the B is along the z-axis, then only if Bx and By are zero, then only the z component of the magnetic field of the magnetic moment is interacting. And therefore, what you're really measuring here are the z component of the magnetic field, right? Of the magnetic moment, mu z. Now, what this experiment is telling us is that mu z is actually quantized. And by quantized, we mean that it cannot take arbitrary components, as in this particular configuration here, which would correspond to a smaller z component. It can only take maximum or negative maximum value. This is for electrons, to say, or from specific type of atoms. Other atoms have provide different shapes like this, which corresponds basically having three configurations: completely up, completely down, or somewhere, or zero. And there are other systems that have even more complicated patterns like this. But the important thing is, let's not deal with this complication. Let's stick to the case, to the specific atoms which provide you with just two peaks for simplicity. We will understand later why some atoms have two peaks, some others have more than two peaks. It will become all clear within the context of quantum mechanics in a couple of months. But as the time being, let's suppose that we focus on those who have two peaks. And we are led to the conclusion that the spin is like coins. You cannot go to your store and buy an ice cream with less than a euro cent price. You don't have nearly euros. You cannot buy nearly euros. You can only buy cents of euros, right? You can only spend cents of euros. So that's the least coin you have. That means that currency is quantized. Well, then when you do wire transfer through banks, who knows what's happening. But as an example, I'm just saying in real life, when you go and pay with cash, currency is quantized. Likewise, magnetic moments of atoms or of electrons is quantized. Okay, that's surprising, but not particularly upsetting. It's something you don't understand. What happens to those magnetic moment configurations in which the magnetic moment is not pointing up or down? Why did they disappear? Why did they all collapse? This is something that makes no sense classically. But there are more things that make no sense classically, as we shall see. Now, suppose we use this device to filter out two beams, one where, this is my original beam, and I can imagine that this is filtered by this in two beams. This is the beam where the spins are up, the magnetic moment are up, and this is the beam where the magnetic moment is down. Okay, so now, suppose now that I place a second device, but now not a line according to the z-axis, but a line according to the x-axis. Well, guess what? This time we are measuring the x component of the magnetic field. And I think nobody's going to be surprised at this point to say that, through the first device, we split, and then, because this is this, and then, of course, here I'm measuring the x component and I split again. But this is the x-axis, so to say. This is the z-axis. So let me draw in red this thing, the magnetic field apparatus. And in black, we have the beams. So not only the Z component, of the magnetic moment is quantized, but also all other two components. Now, here is the X component, and I don't think you're going to be surprised. If you engineer yourself to measure the Y components after that, you're still going to find that it is quantized. So mu X, mu Y, and mu Z are quantized. Quantization of these three objects. Okay, I mean the big leap here is digesting that any of them can be quantized. Once you accept that mu Z is quantized, probably it's not going to come as a big surprise that mu X is quantized too. Why should it? But now comes the extra big surprise, the extra surprise that quantum mechanics provided with, subatomic world provided with. Okay, let's imagine to perform the following experiment. We have my original beam passing through a first magnet that selects the Z component. And then you have Z component, positive Z component filter out. Then you know the Z component of this magnetic moment. Then you go through another similar apparatus by rotating that. Then now measure the X component. And you filter out the X component. And now for some crazy reason, you want to measure the Z component again. Well, you filtered that already, right? So we should know already what the Z component is whatever we measured before, because we have measured the X component after that. So we would expect this to be deflected in one single direction. Instead, what we find is that with perfect symmetric split, we get positive and negative with equal probability. So, summarizing, initial beam, filter out positive Z component of the magnetic moment, separate positive and negative X component, say I focus on the positive X component, positive Z component. I measure again the Z component. It was positive a few minutes ago. I haven't touched it. It should be positive, but it splits as it did before. And now if I can go on, I can take this split and I measure the X component, it splits again, equal probability. So what we are actually concluding from this is the act of measuring the state mu Z or mu X of mu X destroys any information about the state of mu Z. The act of measuring mixes up the states. Even if before my states were purely polarized in one direction, the fact that I measure the other component mixes up the polarization states of the previous direction, the z direction, and now when I remeasure the z direction, they're equal probability. So we are facing an important new phenomenon, which I state in the following sentence. It is impossible to measure by a measurement, to measure simultaneously, or to know, to determine by measurement, by any measurement, the simultaneously more than one component of mu. So this ontologic limitation, not a technological limitation. It's not, this is not a consequence of the fact that we have bad tools. Better equipment would lift this. No. No matter how you do, no matter how you sophisticated, how weak your magnetic field, how precise your measurement of the splitting is, there's nothing you can do. No matter you can do, you can never get more than one component, because once you choose to measure the z component, you completely lose any information about the x component, and vice versa with the y. So this ontologic impossibility is called uncertainty principle, is one manifestation of uncertainty. So already in these first two lectures, we came across a bunch of quantum mechanical phenomena. Delocalization, and interfering destructive measurements and uncertainty, and quantization in this case. All these phenomena are simply not there in classical mechanics, and there is no way you can try to account for them in classical mechanics. People tried everything they could to come up with very articulated and cumbersome explanation of why the double slit experiments was producing those results within classical mechanics, assuming weird interactions through the electrons, for instance, was going around many ways, back and forth the holes, and making all sorts of hypotheses. But none of this cumbersome theoretical explanation could hold on when compared to data. They were all systematically ruled out. And that's how science works. Whenever you encounter a phenomenon that you cannot explain within a certain theory, since the theory has been validated extensively until that moment in order to become a theory, you just don't want to throw it away immediately. Maybe there's something you do not understand of your own theory, and all you have to do is dig deeper in your understanding of that theory in order to explain a phenomenon that at the first sight looks like ununderstandable in that theory. For instance, let me give you an example. People began to realize that our radio waves, and maybe you think there's nothing in classical mechanics that understands that explains what a radio wave is, right? But then people were able to show that, that Maxwell's equation for electric and magnetic fields were actually able to predict the existence of electromagnetic waves, including light or radio waves or microwaves, whatever it is. So I'm not sure this is how historically things went, but the important thing is that here's a phenomenon you initially don't understand, but your lack of understanding was not due to the fact that the theory underneath it was fundamentally wrong. It was just the fact that you did not understand the theory sufficiently well. Similar things are Brownian motion, right? You see, look at particles erratically going in your glass, powder particle erratically going in your glass, and you probably do not understand that in terms of how come this particle move if there's nothing around it. And then you understand, water as a molecular structure, and the molecules of water are actually heating because of thermal agitation, that grain of powder, and producing this erratic behavior. And this is an example of, it wasn't classical mechanics to be wrong in this case, at this scale. It was just that our understanding of that specific physical system was not complete. So people, at the beginning tried very, very hard to make sense of these experiments without raising hands and say, there is an uncertainty principle and we just don't have the right theory to account for that. And even Einstein himself, who played a crucial role and won a Nobel Prize for contributing to the development of quantum mechanics, never believed that quantum mechanics could be a fundamental theory. He thought that basically the uncertainty that we observe is basically due to the fact that we don't have complete control on the system. We don't know everything there is to be known about the system. So the uncertainty is an emergent phenomenon for Einstein, resulting from the fact that we don't measure the system and there are variables we don't get access to, which provide stochastic behavior and certain order. However, this point of view of Einstein was systematically proven wrong in 70 years of experiments, and there is no doubt today that Einstein is wrong. That simply there is some completely different behavior from classical mechanics, and you just have to accept it. Okay, so we're coming to a point to understand a few things here, and there's more phenomenology that can be understood in quantum mechanics, can be revealed by looking at microscopic particles. And one of them is the photoelectric effect. Well, you shine light. Remember our understanding of classical theory of the atom should work, right? Or any bound system should work. You have an energy, you have this is my potential and effective potential. So let me draw this a little bit better. We have an effective potential. So we have my atoms, electrons, and each of them, if you neglect the interaction between the electron, and you close your eyes for a moment to the fact that these atoms are unstable, because maybe we are thinking, maybe we still don't understand why they're stable. Maybe we're missing something, and the atoms can be stable, but we just don't see why. So let's take this opportunity open for a moment. Then we have the electron, has a given energy, and we expect that if we shine the electron with sufficiently intense light, we give the electron more energy. And we give this energy, and we should be able to free the electron. So the intensity of the light should be responsible, since in the classical electromagnetism, the energy carried by light is proportional to the square of intensity. Then I would imagine I use, in order to get an electron out of the atom, all I have to do is take whatever light I have and double its intensity. Maybe if I was shining my atoms with one lamp, I put 10 lamps of the same type, and I multiply by 10 for the intensity, and the electrons should go. After all, when we are in the sun, when the cloud is shielding the sun, just part of the radiation comes, the intensity of the light decreases, and I feel less hot. I absorb less energy. So why shouldn't the electron do the same? And in order to kick out an electron from the atom, I would expect that I need heavier and heavier, more and more intense light. However, people began to understand that when they began operating with monochromatic light, they began to understand that this was not what was happening. Some frequencies of light, some colors, were not resulting in any electron being emitted. Now, we might say colors, colors is a word that refers to visible light. Let's be a little bit more general here. It could be visible ultraviolet, doesn't matter. X-rays. The important thing is that specific wavelengths. Basically, if you shine light over a given system and with the wrong frequencies, no matter how intense that light is, the electron is not kicked out. However, if you choose to shine the electron with the right frequency, then the electron is immediately kicked out, and the number of electrons that you kick out from a sample becomes proportional to the intensity. And the explanation for this, which was basically due to Einstein, was that the energy carried by light doesn't go only with intensity. Actually, the energy carried by the basic explanation of light was made of individual particle-like objects, just as much as the electron has a particle wave behavior, the light has a particle wave behavior, but the energy of this object that Einstein called photons were proportional through the Planck constant to the frequency of the light. So if you get the wrong frequency, you don't have the energy to kick out the electrons. And you really need to have the right energy, therefore the right frequency, to push the electron out of the atom. But since the frequency is the same for all atoms, it means that all the electrons in that atom have the same energy. There are some magic values of the energy in atoms, which reflect themselves in magic frequencies that depend specifically on the atom. So this experiment basically implies the quantization of the energy allowed to have in a system, and the fact that the energy of the electron is proportional, of the photon is proportional to the frequency. So you see, if the electron was allowed to have any energy here, then basically with any frequency, I could kick up some electrons, because I would keep, with a small energy, say E prime equals H nu prime smaller than H nu, that's my new energy. I would be able to kick out the electrons that have this energy, while with larger frequencies, I would be able to kick out the electrons which have more energy gap. And that's not what you see. Basically, there are only a few magic energies and therefore photon frequencies, which tells us that the energy of the electromagnetic radiation comes with a frequency, but also that the energy levels that electrons can take in an atom are quantized. And the particular levels that an atom or a molecule has, meaning the particular frequency of light that you can actually absorb, are a signature of that particular system. And that's why, that's how people, tell you that a given star is made by these and these and these and these and these substances. Or a planet is predominantly made of, I don't know, say, chloride or oxygen or whatever it is. Because each atom or each molecule, depending on if you have atoms or molecules, they have their own signature, their barcode. And the barcode is the typical energies they have. And the frequencies that can be absorbed are only differences proportional to differences in energy. So basically, in other words, the light that can be absorbed by an atom corresponds to frequencies proportional to the energy difference between these energy levels. So H nu, the nus that are allowed are only differences between these magic energies. So if you pass a light shine through a substance containing atoms, and then you polarize, use a prisma in a Pink Floyd with Dark Side of the Moon style to separate the frequencies, you'll discover that there will only be a few lines in the spectrometer. And these few lines are the lines that are associated with energy differences characteristic of that very system. Because that's the very notion of energy quantization. And no need to say, people tried hard to account for energy quantization in classical mechanics, failing, and then try to minimally tilt classical mechanics in order to accommodate at least the presence of energy quantization by introducing a little bit more principles. This was called the old theory of quanta, where people took basically the same theoretical framework of classical mechanics and tried to add one more principle. Maybe only certain orbits in phase space are allowed and corresponding to certain energies. And they try to introduce tilting and variation of classical mechanics to minimally perturb it, but keeping the same notion of Hamiltonian, Hamilton's equations, and blah. But ultimately, none of these attempts were completely successful and were able to explain the whole phenomenology that was emerging from experiments. So the result of that was, in the end, that people had to abandon these ideas and accept the fact that they had to rebuild an entirely new theory based on completely different concepts. And that's what we're going to do starting from next lecture. We're going to go back on the double slit experiments and try to see what can we say, what does a theory need to be made of in order to hope to be accommodating for these new evidence. And we'll have to define the concept of state of the theory, the concept of quantization of motion. Ultimately, we'll reach to move the first steps into quantum mechanics. Okay, that's it for today. Let's continue next slide.